opens SimExpert in the Structures workspace. To create the geometry, click on the Geometry tab. Since the cantilever can be analyzed using flat elements, we are interested in surface elements and geometries. Under the Geometry tab, we find the Surface group. Select the Planar Creation tool. Note that other methods of creating a surface element are also available. We create a surface using a single point initialized at the center of the workspace, which is the center of the surface as well. We select the XY plane to orientate the plate along the XY plane of the Cartesian coordinate system. As per the measurement shown, we use a length of 300 mm and a width of 200 mm.
It should be noted that the apply function executes the function but keeps the form open. The OK button executes the current function and closes the form. Do not click the OK button after clicking the Apply button, since it might result in duplicate actions.
Press F to fill the screen. Now we create a hole in the center of the plate. Still under the Geometry tab, under the Features group, select the drop-down of the Hole tool, select Add. Select the surface, specify the hole diameter 75 and the coordinate at the center of the surface, which is 0, 0, 0. To see the file set tree, click on the plus tool on the leftmost pane called the Model Browser. Now you create the finite elements by meshing the geometry. For more information on the meshing, refer to the 5 meshing presentation. Under the Meshing tab in Auto Mesh group, select the Surface tool. Select the surface to be meshed. Under Element Size, type in 20 to create elements that are more or less 20 mm in length and width. Under the Mesh Type drop-down, select Quad Dominant. This will ensure a mesh pattern consisting of mainly quad elements. Under the Mesh Method drop-down, select Paving. This method makes it possible to mesh any complex geometry by first meshing the edges around the hole and then further inwards. Check the washer around hole checkbox on the max hole perimeter per element size, type in 48. Under Layers, type in 3. This will ensure that there will be 3 layers of circular pattern mesh around the hole. Remember to save your work periodically. Let us save our work. Let us create the material and then assign that material to the elements of the geometry. Under Materials and Properties tab in the Materials group, select Isotropic. Under Name, type Steel. Then by pressing Tab, we will select a different box. For the Young's modulus, type in 207,000. Since we have the unit set in millimeters and newtons, this corresponds to 207 gigapascal. Under the Poisson's ratio, type in 0.3. Press Enter. Still under the Materials and Properties tab, we find the 2D Properties group. Select the Shell tool. Change the name to Plate Material. Under Entities, hover the cursor over the selected text box. A selection tool will appear. Deselect Surfaces, Sheet Features and Parts. Now the elements will be selected. Under the same tool, go to Select All and press the left mouse button. Notice the geometry is highlighted with elements. Select the Material selection box, select the drop-down and select Steel. Under Thickness, type in 1, press Enter. Under the Element Detailed Drawing, select the drop-down and select 3D Shell Thickness. Notice the thickness of the geometry is now rendered. Deselect by clicking on the 3D Shell Thickness again. Under the View drop-down, select Top View. Now we want to constrain the model and assign a loading case. Under the LBCs tab in the Constraints group, select Fixed. Hover over the Entities box and deselect Nodes and select Curves. Select the leftmost curve, select OK. Under the Loads group, select Force. Notice that the selection would be nodes. Select the rightmost bottom node on the model. Under Scale Factor, type in 50. This will assign a load of 50 newtons to the node. Under View drop-down, select ISO View. Under Static Selection tab, Z direction, type in -1. This will ensure a load of 50 newtons to be applied in the negative Z direction. Press Enter. Now we do a quick check to determine if we got all the aspects needed to complete the static analysis. We got the geometry. We measured the geometry. We created a material and assigned the material. We constrained and loaded the model. Now we need to create a Nastran job to solve the problem. Right-click File Set under the Model Browser pane. Select Create New Nastran Job. Under Job Name, type Cantilever. The solution type should remain a Solve 101. Under Solver Input File, select the folder where you saved the model. Select OK. Under Simulations, under the file set, right-click on the Nastran job renamed Cantilever. Select Run. Check the FF6 file to make sure the solver is done and that there are no errors. To do this, we search the file for Fatal. If the search for Fatal returns no errors, the job was solved successfully. Any fatal errors that are returned in the search for Fatal should be rectified before the solver is run again. Remember that there will be no results if a fatal error has occurred. Now we can attach the results. Select File and then select Attach Results. Make sure the file to be attached is the Nastran job name with an XDB suffix. Press Enter. Under the Results tab, select Deformation. To view the translational displacement, select Displacements, Translational from the Results type box. Select Update. Close the window. To view the von Mises stress fringe on the deformation plot, select Fringe Results. Select Stress Tensor, von Mises, and then Update. This tutorial was brought to you by STEC.